Namaskaram to everyone. Welcome to series of lectures on finite element method. Today we will discuss about strain displacement matrix for two-noded 1D bar element. So we have previously discussed importance of finite element method. Whenever we have a complex problems, we try to convert that one into finite elements and we work on each element. Then we'll assemble all together and we'll get the final solution by assembling it. So today we'll discuss about two-noded 1D bar element. Suppose if you are considering an object, a bar, first this bar to be converted into a finite elements. So I am considering 1D uniform elements. Like this, I am converting this entire bar into a uniform number of elements, and each element is a one-dimensional element. Suppose if you consider one element from this, that element looks like this. And throughout the length of this element, the cross section will remain same. Suppose if I take one element in a large scale, that element looks like this. Right. So this element is now 1D element which is having two nodes. So it is node 1 and node 2. So this element is having a displacement q1 at node 1 and q2 at node 2. So now I have to develop the strain displacement matrix for the given element. So whenever you want to get a strain, the strain comes from the displacement. So if you take the derivative of the strain, derivative of the displacement du by dx, then we'll get the strains. And it is for one dimension. In general, for a three-dimensional entire strain matrix, it looks like this: dou u by dou x and dou v by dou y and dou w by dou z. These are the direct normal strains, and we have dou v by dou z plus dou w by dou y, which is a shear strain, and we have dou u by dou z plus dou w by dou x and dou u by dou v plus dou v by dou x. So this entire 6 elements of strain will be there for when you consider an object in a 3 dimension. Since here we are working on a one dimensional bar, so we consider that strain is only there in this x direction, so that will become dou u by dou x. Since the dimension is only in the x direction, you can write this one as du by dx. So essentially got the strain expression, strain in direction, as du by dx. So that means how the displacement changing in the direction of the x. So we have considered this as a 1D bar element which are having two nodes 1 and 2, where the displacement is q1 here and q2. So if you want to find out this strain, I must know what is the displacement u. So u is basically the displacement anywhere within the element. Usually we will get the displacement at the node, since we have two nodes here, node 1 and node 2. So the displacement is q1 at node 1 and displacement is q2 at node 2. Suppose if I want to find it out somewhere within this element, a displacement, that displacement I am considering as u. So how I can find out this displacement? If I want to find out this displacement, I have to consider that the displacement depends upon the q1 and q2 and how the displacement is varying within this element. If you want to know the displacement, how it is varying in this element, that we have to consider a shape function. So shape function is a mathematical expression to give how physically the system changes within the element. Since here it is a structural problem and here the variable is a displacement. That means here the shape function will give how the displacement varying within this element. Suppose if it is a thermal problem, then how the temperature is varying within this element. So shape function will give the variation of the field variable within this element. So the shape functions plays an important role in finite element method. So the detailed discussion was already given about shape functions in the previous classes. Please kindly refer to that lecture. So here, if I am considering the shape function here, so if you want to know the displacement u, the displacement will be n1 and q1 plus n2 q2, where this n1 and n2 are shape functions. And now this n1 and n2 are the shape functions. The shape functions can be described in a different coordinate systems. We have already discussed what are the different coordinate systems. Right? We have discussed that that is a Cartesian coordinate system. That Cartesian coordinate system will have like a local coordinate system and global coordinate system and a natural coordinate system. So mostly the shape functions are derived either in Cartesian coordinate system or in natural coordinate systems. A detailed way how we will get the shape functions in Cartesian coordinate system and natural coordinate systems are already discussed in the previous classes. So today I will try to directly apply these shape functions without giving the detailed description of it. So first I will try to derive using this Cartesian coordinate system. So when I am writing u is equals to n1 q1 plus n2 q2. So now I am writing this n1 is nothing but 1 minus x by L and n2 is nothing but x by L. So these are derived previously. You can refer to that class. Now if you want to describe this d cube by dx, so that will give d by dx of n1 q1 plus n2 q2. And q1 q2 are the displacement nodes which are the constant. So this, if you write it, you can write this one as q1 dn1 by dx plus q2 into dn2 by dx. And if you write this q1, so differential of dx into n1, which is nothing but 1 minus x by L plus q2 into d by dx into x by L. So you will get this one. We do it, you will get minus q1 by L. I'll write it in here. So I'll get this strain du by dx as minus q by L plus q by L. And if you rearrange these terms, you can write them as 1 by L by L to q1 by this q1 and q2 is equals to your du by dx, which is nothing but your strain. And this minus 1 by L and 1 by L, which we call this one as B. So I can write this expression as strain, that is equals to B into this q bar, where this B is called strain displacement matrix. and q bar is your displacement vector. So I can write this B as 1 by L minus into 1 by L, where this L is length of the element. If you observe it clearly, the strain displacement matrix here, that is 1 by L minus 1 by L and L by L, 1 by L. So here there is no variable existing in this. That means within the given element, this strain displacement matrix is constant. So we can say that this E is nothing but BQ. So that means the strain within the element is constant. So that's why we can call this two noded 1D bar element as constant strain element. Constant strain element. So this is by using your Cartesian coordinate system. Suppose if you want to derive the same by using natural coordinate system. Right. So you will write this U is nothing but N1 Q1 plus N2 Q2, where N1 in natural coordinate system you can write it as 1 minus zeta by 2 and N2 is equals to 1 plus zeta by 2. So again, how we got this 1 minus zeta by 2 or 1 plus, this is again discussed in the shape function classes. Right. So now if I write my strain, that is equals to du by dx. Since here we are using the natural coordinate system, then we have to use this chain rule to write this one as du by d zeta into d zeta by dx. Because here our displacement u is now, it is a function of your natural coordinates. So by using this chain rule, you can write this strain as du by d zeta and d zeta by dx, right? And you know what is this du by d zeta, because you have this expression. So I can write this du by d zeta is nothing but your u, that is n1 q1 plus n2 q2, and it should be multiplied by d zeta by dx, right? And we know what is this d by d zeta to n is nothing but here 1 minus zeta by 2 into q1 plus 1 plus zeta by 2 into q2 and multiplied by d zeta by dx. This is all is equals to your strain. Hope this is clear. So further, you know q1, q2 are the displacements at nodes 1 and 2, as I have already given the 1D two noded element where node 1 and node 2. So here it is q1 and here it is q2. So if you write this expression, you will get this one as q1 d by d zeta to 1 minus zeta by 2 plus q2 d by d zeta 1 plus zeta by 2, entire expression multiplied by d zeta by dx, right? So if you differentiate this one, what you will get? You will get this one as minus 1 by 2. So I'll get this one as q1 by 2 plus q2 by 2 multiplied by d zeta by dx. Now you need the term in terms of natural coordinates and Cartesian coordinates. So, we will write that expression when you are considering this element, so where it is node 1 and node 2, and here in Cartesian coordinate system at node 1 it is x1 and at node 2 x2. In natural coordinate system it is psi, that is equals to minus 1 here, here it is theta is equal to plus 1, right, and at the center we know, so that theta is equals to 0, right. Suppose somewhere I want this x from here, this is my x, right, then this will be my zeta. And if you develop the correlation between the natural coordinates and the Cartesian coordinates, I can write this expression with zeta. At this point it is zeta minus of, here the zeta value is minus 1 upon the total length of the element, that is plus 1 minus of minus 1. That ratio is equals to your x minus of x1, which is here it is your x, and here it is x1 by x2 minus x1. And if you use the simple math, it will give that zeta plus 1 by 2, that is equals to x minus x1 by x2 minus x1, right. From this you can write zeta plus 1, that is equals to 2 times of x minus x1 by x2 minus x1. So you can write zeta 2 times of x minus x1 by x2 minus x1 minus 1. So we develop the relation between the natural coordinates and the Cartesian coordinates. Now we need the d zeta by dx. So if I differentiate it, this d zeta, I will get this one as 2 by x2 minus x1 to dx. So we know what is x2 minus x1. x2 minus x1 is nothing but the length of the element. So I can write this one as d zeta is equals to 2 by L into dx. So I can write this one as dx d zeta by dx is equals to 2 by L. Now we substitute this one in the previous expression. If you see here, what we got here, this d zeta by dx, here we have to use that, this d zeta by dx which we got. So that only we are trying to write it in this expression, d zeta by dx. So just I will put it this one expression in the previous case, this d zeta by dx. So if I put this expression here, I will get this expression, I will write it here, zeta is equals to q1 by 2, minus plus q2 by 2 multiplied by 2 by L. So if you simplify it, so this 2 and this 2 will get cancelled. So then we'll have then expression minus q1 by L plus q2 by L. So if you rearrange these terms, I'll get minus L by L into q1 q2, where again, so where here this can write it as E is equals to again B into q bar, where this B is again nothing but this B we written already as strain displacement matrix. So this way we have derived the strain displacement matrix by using Cartesian coordinate system as well as natural coordinate system. And why this strain displacement matrix is important? Because when we are trying to derive our stiffness matrix, the strain displacement matrix B plays an important role. That's why it is important that first we have to understand the strain displacement matrix, so that When we substitute the strain displacement matrix in our stiffness matrix, we can easily find it out, the stiffness, element stiffness matrix of a given member or a given element. Thank you. Thank you for attending this class.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.